Welcome to the first law of thermodynamics. So I'm just going to start off by defining what a control mass is. Now, a control mass is simply just any single amount of mass that does not change, so it's going to be the same mass, but will undergo a process. Now, an example of this will be a piston, and we're going to be looking at a piston problem later on in this video. But first, I'm also going to define internal energy. Now, I briefly mentioned this in the video about reading thermodynamic tables, and we denote internal energy with a U. Internal energy is the total of all the energies, the total of all in a system, and this includes things like the kinetic energy of all of the particles, even their potential energies, and even includes the things like bond energies of molecules in the system. So it's literally the sum of all of the energy. So now that we know that, let's define what the first law of thermodynamics is. Well, the first law of thermodynamics more or less says that energy cannot be created or destroyed; it always stays the same. And to put this in an equation, we have the heat transfer, that is heat going into or out of a system, minus the work that system does or is done on it, and equals the difference between the internal energy of state 2 minus the internal energy of state 1. And this also equals the mass times the specific energy, internal energy of 2 minus specific energy of 1. Now, the only difference between specific internal energy and internal energy is this is just internal energy per kilogram, and this is the internal energy. So Q is, gaining or losing heat. If Q is positive, we gain heat. If Q is negative, we lose heat. And in the last video, we talked about work. So if work is positive, we're doing work. So you see how we have a minus sign? So it's energy in minus energy out equals the change in energy, which would be true. You can also think of this as Q minus W equals the change in energy, because that is what U2 minus U1 is. U, internal energy, is all of the energy, so the energy in state 2 minus energy in state 1 has to be, the change in energy. If it goes up or down, it's going to be shown in the change in internal energy. So let's move on and do a problem. Alright, so I'm going to define state 1 as this piston, and it is filled with saturated H2O at some arbitrary mass on top. The mass of this H2O is 0.2 kilograms. And the pressure in this piston is 0.1 megapascals. And its quality equals 0.7. And now I'm going to, so this is saturated, because we have equality, and I'm going to heat this up. Heat is going into this piston, and I'm going to heat it up until it is completely a gas, until its quality equals 1. So it's going to expand. It's still H2O. The mass is still 0.2 kilograms. That has not changed. We're not adding any mass. Its pressure still is 0.1 megapascals. And its quality is now 1. And I am asking, how much heat did I put into the system? Now, if you want to try this problem yourself, pause it now, try it, and if not, I am going to do it for you right now. So let's start off by finding out what the volume is of state 1 and state 2, because we're going to have to fill in the gap in this equation. This is this is the first law of thermodynamics. We just went over it, and we're first going to find out what work is. And to find out what work is, we're going to use the equation for work that we did in the last video. So we know pressure, that was given, but we don't know V2 or V1. However, we were given its mass and 2 properties of each state. So we can look up what the specific volume will be for each one of these and multiply that by mass and get volume. So let's start off. We know. Now if you just look up the values in the tables, I will just sort of skip ahead. We know the specific volume of state 1 to be 1.186 meters cubed per kilogram. Now that's just done by using the quality and the specific volumes for the gaseous state and the liquid state. So we know the volume equals 0.237 meters cubed. And now we have V2 equaling 1.694 meters cubed per kilogram. We multiply that by its mass, and we get 0.339 meters cubed. This, you might notice that this is the specific volume for its gaseous state, and that's because we have nothing but the gaseous state of H2O here. Next, we're going to find the internal energy of each state, because we also need to know these 2 values in order to find Q. So U of F, U of G, and the internal energy of 1 is 1879.48 kilojoules per kilogram. U2 is simply just going to be 2506.1 kilojoules per kilogram. Again, the exact same thing as the internal energy of its gaseous state. And I do believe that is enough to find out heat, Q. So let's solve for Q. Q equals work plus mass times U2 minus U1. So Q, oh wow, I jumped the gun there, didn't I? We have to find out what work is. Work equals P V2 minus V1, which equals 0.1, that equals 100 kPa times 0.339 meters cubed minus 0.237 meters cubed, which equals 10.2 kilojoules. So we'll just put this in for W here. 10.2 kilojoules plus 0.2 kilograms times 2506.1 minus 1879.48 more this, and the units here didn't have room, are kilojoules per kilogram, and as you see we cancel out the units and we're left with kilojoules. So the heat transfer is 135.5 kilojoules, and that is how much heat we put into this system. Now, if you had any trouble following my work, please tell me. I can redo this problem. I can come up with another one, and we can hopefully make sure you understand this. Until next time, I'll see you around.